Hey everyone, and welcome back to Low to High Level. This episode's intro is a little weird because I'm in a different location. I'm just in a different room of the house. Nothing crazy. So, we've taken all of our systems together and we've created a functional ALU, or Arithmetic Logic Unit. Today, we're going to be going the extra mile. We're going to take some basic gates, we're going to create what is called a register. This is a single byte in memory that we can use to access things. And if we can access a little bit of memory, we can run programs. So we're going to turn this ALU into a functional CPU, or Central Processing Unit. That is our goal for today. And boy, are we going to make it, because this video will not end until we make that goal.
To store data, we need something called a register. And the bare minimum to have a register is a little bit of data. What we're creating now is what is called a D flip-flop. So we take these NAND gates and we pipe them together in a very specific format that allows us to create this D flip-flop. And the way that it generally works is by looping itself back into each other. You can set or reset data. So there's your D flip-flop. Similar to how we made those 1-bit systems and we upgraded to 4 bits, we're going to do that again. We're going to have 4 bits of input and 1 set or clock system. So with that, we have our 4-bit D flip-flop. And just like we've been upgrading our 4-bit systems to 8-bit systems, we'll do the same for this D flip-flop. We'll take our 4 bits of input and we'll put them together and create 8 bits of output. Perfect. With this 8-bit D flip-flop, we can do a few things. We can allow input or output, as well as our original clock signal that we used to set, and with that, we can enable or disable the ability to write or read from the system. That will greatly make this easier for us, because now we have a register. Let's take a little break from that register information, and we're going to look at what we can do. With our ALU, we have certain things, and we've created a 8-bit register. So with this register, we want to figure out what we can do and how many registers we have. So in architecture design, you want to figure out a number of registers. Here I decided, I'll have an registers A through F as well as a stack pointer. That may change, I'm not certain. But here's what some potential assembly could look like. So say I have a set, so I can set a value, or I can move values between registers. That would make it a little easier to write some code. And we can add using 3 registers. So one would be the value that we're storing, and the 2 values we're adding. So with these bits of information, we can do things. And this is me figuring out, hey, these are some extra commands that I can run. And if I can run certain things, I can create some functional code. I'm dancing around my keyboard here, but that's me being silly. Eventually I'll come up with some ideas and get going. So if I'm looking at my instruction, I'm thinking it'll be 4 bits for the main instruction, 4 bits per register. Since we don't have that many registers in our CPU, we don't need more than 4 bits. And we don't have that many instructions in this current design, so that's fine. We'll continue making those out, and here's the actual instruction. So the actual bit code for these instructions are what that's going to be. I'm not certain what it is. I'd have to look at my simulation to get that bit, but I do know for certain that it ends at 7 and it goes to 8 or 9. I can come up with other ones, and here's my register numbers. I'm starting with 1 because I'd like the ability to write to a 0 register that has nothing. So say I want to write to nothing, but I want to add because who knows why. That gives me that opportunity. Because my code does some weird things, I'm going to look at a different way of having my registers. So I want to figure out, how can I have multiple outputs from a register so I can read multiple times and input twice. The way I want to do it in my wiring is I want to have two buses. So with that, I can say, okay, here's my register, and why don't I just output to enable lines? And if it's enabled, it'll output to that bus line. And if I can only have one register enabled per bus line, I'm fine. So that gives me the base concept of how this is going to work. So I'm outputting my data to each pin on the register, and I'm getting my input data and saying, hey, if I want to read, I can read to that register. And that's great, but what if I want to write? I probably have to have some sort of write enable, but the register by default, in the way that we've designed it, already has that, so I don't need to worry about that. So I can choose to write, I can choose to read, and when I read, it'll do everything I need it to do, which is great. So there's me outputting data, and both pins are enabled. So that's my register with two outputs. And there we go. And with so many outputs, there's a lot of stuff you gotta do. So I'm updating my selector to allow for a couple other things, and here's my using that selector to create memory. So here's my two output registers, and I want to be able to select certain registers within it. So select the output, select the inputs. So that's me wiring that up and getting it there and merging it all together, so everything is happy. It's not perfect, but it's good enough. So now that I have these selectable registers of that, I can put a bunch of selectors together and create all of my registers on one chip. That just makes it a lot easier to read and write to memory and deal with the system. It's not the most difficult thing to do, but it's quite complex, especially looking at that wiring. And me having to OR everything together in the end to get it to fit, it's a bit messy, to say the least. But in the end, after I got everything together and put everything out, I have two outputs from a bunch of selectors of each register. There we go. With our big design that we've put together, we want to be able to control different bits that we're dealing with. So I'm grabbing a bunch of gates, and I'm going to put them together in a function that allows me to control 4 inputs into a certain number of outputs. So here's me looking at this data and trying to figure out what I'm going to do with it. And I'm kind of losing my mind. I'm like, oh, can I fit an ALU in this? Can I do this? Can I do that? I ended up saying, screw it, I'm just going to redo it. So here's my information, trying to fit what I can, trying to understand what my problem is, because I have no clue. And here's me saying, okay, my lowest bits, if they're together and that's not enabled, then by all means, we're controlling the CPU. If that highest bit is enabled, we're doing data. So, going through that, I'm filling those in and saying, okay, if it's low, then we're controlling CPU. If it's high, we're doing something else. And with that high bit of data, we're controlling registers. Either we are setting to it or we are reading from it. So looking at this, we are setting, or if we go to another case, we are reading. So since we're reading, we'll have to read. So I'm going and doing specific cases and saying, okay, this is what I'm trying to control, and this is what I'm doing. But I'm rambling, so I'll just let you see it. There we go. With all these control bits that we've finally put together, I'm gonna set up a little system. This is gonna be our central processing unit. So that big CPU that we've been working towards all this time for the last 5 episodes. We are finally putting it together and making our CPU. So we have our first bit, which is always going to be control. So that is what specifically we are doing. Right now I'm trying to figure out how do I want to wire up my registers. So I gave up on that pretty quickly and said, you know what? Control bit. So I can easily plug in the ALU. That's easy. And now it's just a matter of saying, okay, what data goes where? So putting that in, I can write and handle things and figure out what's doing and dance everything around on my keyboard and maybe smash my face into it a few times to see what works. Eventually I decided, hey, I could enable the registers based on what's needed, and some cases it may work, some cases it may not, but that's all a matter of figuring out what works. Testing things, going back, going forth, and seeing what is there. So I'm putting these AND bits together and getting everything there to say, hey, what will work? Did I miss up something? And yes, I did. I usually do mess up something when I'm trying to figure out all this. It was all in one take. So here's me wiring up my registers to my ALU and seeing, hey, can I get this going? And eventually I did. Now I'm taking all my outputs and figuring out what goes where, who does what, and everything goes back into the registers, because that's how an ALU works. It's just a big loop of wires that makes no sense whatsoever, unless you put it together. So getting all these things together was a little bit of a pain, but it's all about that journey. So functionally, I am testing to see what's working and what's not, and I'm thinking something's going terribly wrong, like usual, and I'm trying to figure out where my issue is in the wiring, and not 100% sure, but in my testing, it's looking better and better. Eventually, I got there. I created the ultimate thing for my evil plan. Yes, I'm Dr. Doofenshmirtz now. The CPU. And to test the CPU, I want to make sure that everything works well. So I put all the chips on one new chip just to wire it up and figure out what works. I have all 16 bits of my command wired up, as well as a clock signal, because everything runs on a clock, and that's external to the CPU. So slowly I'm wiring things together to see what works. It takes a lot of time, but we'll get there. Once this was all wired up, I went and tested a few commands. Here I'm trying to figure out a couple of registers to read and write from, as well as a command and clocking to it, so that should write some data to the register and set something. And now I'm trying to see if I can do some addition, and sure enough, I can, and it's writing more data. So as I keep testing this and figuring out, okay, is this working? Is this doing what I need it to do? I'm checking and seeing if it does, and sure enough, it does. We now have a functional CPU.
And we made it. We have a CPU, a central processing unit that we can run programs on, or at least theoretically. So this concludes our section on Boolean logic. We have built a functional CPU out of just Boolean logic. Now, we could mess around with this a little more and go further and further, but judging by the fact that we have a functional CPU, I don't think we need to go that much further with it. We know how we can make RAM. We essentially just take a bunch of registers and we add them together infinitely. And we could have as much RAM as we'd ever want. But this program is limited in what it can do. So our next steps are going to be creating some sort of emulator and emulating our CPU so we can run some programs. And that will be our next goal. All right, I think that's it for this episode. If you liked it, be sure to subscribe. And I'm going to show somewhere on the screen another video you might want to watch. All right, bye.